So in this session we are going to discuss about the specification of tokens, how we are specifying the tokens. Before going to know about what is token, how we are identifying the token, first of all we need to know the attributes or the characteristics of the token. So first of all we need to know an alphabet. It is a finite set of, alphabet means it is a finite set of symbols, whether it may be a alphabets or alphabetical characters or numbers or digits or hexadecimal numbers. And then if we combine these alphabets, we are going to make a string. If we are specifying these strings along with the operators, then or else we may have some statements. Like for example, if we are having some characters, then if we combine the character, then we are going to make use of a string. In the same way, if we are having finite set of strings, then we are having the language. So the language may contain some set of strings as well as operators. So here, if we are given with a source program, so the lexical analyzer will identify the token. So how from the source program it will take the string and it will match that particular, that means here the longest match rule means whenever a white, until and unless a white space or operator or a special character has been encountered, we need to read the characters from the input source program, and then that should be matched with the given set. That should be matched with a given token. Okay. So here we have discussed about alphabet. Alphabet is a finite set of symbols. Those may be either numerics or else digits, or English language alphabets, or else hexadecimal numbers. If we combine these alphabets, we are going to make these strings, and if we combine these strings, we are going to generate the language. So that here this language means not only normal, not like general language, general communication language. So here we are going to have whatever the set of strings, whatever set of alphabets we are going to make use. Like for example, in English alphabetical letters, we are having 26 letters. But we are not going to make use of all those 26 letters in our formal languages. We can make use of only 2 or 3 alphabets. And from those alphabets we are going to make these strings. So how many different strings we are going to make by using those 3 or 4 alphabets, whatever we are going to make use. So those strings can form a language, and from that language we are going to identify the tokens. So generally for identifying the tokens, we will have regular expressions and regular languages. What is meant by regular expression is, if we are in a particular language, here the language contains some set of strings over a set of alphabet, so that in that particular language, whatever the strings we are having, so we are having a common expression for representing all those strings in that particular language. That is that common expression is called as regular expression. So whenever we are having a regular expression, according to that particular regular expression will represent the regular language. So we can perform different operations whenever we are having a language, so that we can perform different operations on the languages. One is union, concatenation and clean closure operation. So here as we know that if we are having 2 different languages, for example a language contains L1 contains the strings which can be formed by using A and B, and the language L2 contains the strings which can be formed by using 0 and 1 or 1 and 2. So that what are the different operations we can perform on those 2 languages means we can perform union operation on L1 and L2. Here L1 contains the strings over 0 and A and B, whereas L2 contains the strings over 0 and 1. So that we can perform union operation, concatenation operation and clean closure operations on these 2 languages, L1 and L2. So if we make use of union operation on L1 and L2, so that what is the action we are going to perform. So if L1 contains alphabets, the strings which can be formed by using A and B. So here like this we can perform, whereas L2 contains 0 and 1. So what are the operations we are going to perform is L1 union L2. Here we can combine all the strings of L1 as well as L2. So we are not concatenating, just we are combining AB, AAB, ABAB and so on. 0, 1, 0, 0, 1, 1, 0, 1 and so on. So we are not concatenating them, just we are adding these two, like all the strings, that means L1 union L2 contains all the strings of L1 as well as L2, whereas L1, this is a union operation, then we are concatenating L1 L2, so we can write it as L1 L2. So in this we are concatenating the strings of L1 as well as L2. AB is concatenated with 0, next AB is concatenated with 1. Next AB is concatenated with 0, 0. Then AB 1, 1 and so on. Next second string AAB 0, AAB 1. Like this we are going to perform concatenation operation. In the same way, already we have known about clean closure operation. So if we are having a particular language L1, then clean closure operation can be specified by using the star operator. So if L1 star means 0 or more occurrences of L, 0 or more occurrences of strings in L1. So for example, if A is a string in L1, A star means then epsilon, A, and so on. Whereas if we are having multiple number of strings, like multiple character strings, then AB, so next AB, and so on. If it is A, B star, so there is a difference between AB whole star or AB star, then it is epsilon A. So here this star operator, this clean closure operator is only for B, so that this B can be repeated for 0 or more times. So first time I am taking this B occurrence for 0 time, so that the string will be A. Then one occurrence AB, ABB, and so on. These are the operations we are. So this is about clean closure operation. So these are the operations we can perform on. That means union, concatenation, and clean closure operations can be performed on a particular language. Okay. Next, what are the notations for union? It is U symbol, then concatenation and star closure operation. So what do you mean by valid token? So if you are given with a regular expression, what do you mean by a valid token? Means here star means 0 or more occurrences of X. As we have already discussed, A star means 0 or more occurrences of A, and A plus means 1 or more occurrences of A. The regular expressions. So here the regular expressions is an important notation specified for specific patterns. So, regular expressions means for specifying a stream of strings. Some set of strings generally form a regular expression. This regular expression will be used in the regular language. So whenever we are given with a language, then that particular language contains some set of strings over the alphabets. So that will form, that means if we want to combine all those strings together, then we can generate a regular expression. So how we are going to generate a regular expression from the given set of alphabets means, suppose if epsilon, here this is an epsilon symbol, if epsilon is a regular expression over the language, so that only epsilon will be there in the given language. If a is there, if a is a symbol in the as a regular expression, then a will be there in the language. Suppose if we are having a star, then all combinations of a's will be there in the regular language. For example, if epsilon is a regular expression, then the language contains only epsilon. Why? Because epsilon is an empty string. So we are not having any symbol or any string in the given language. If a is a regular expression, then the regular language contains only a. Whereas if it contains a plus is a regular expression, then we can write a and so on. That means all combinations of a's will be there in this particular language. So according to the specification of the regular expression, we can will have the strings in the language. Suppose if it is a star, then the language contains the strings as epsilon, because star means 0 or more occurrences of a, whereas plus means 1 or more occurrences. So at least one occurrence should be there. But here star means 0 or more occurrences. If this a has occurrence is 0, then automatically it is an empty string. So that we need to specify that with epsilon. Then a, and so on. So like this we are going to specify the regular expressions. So here we, as we have already discussed, plus means 1 or more occurrences, star means 0 or more occurrences. Along with these symbols, we are also having one more symbol called as question mark. So here the question mark means like 0 or 1 occurrence. So whenever we require one occurrence, only one occurrence, we can go with question mark symbol. If we require 1 or more occurrences, then we can go with plus symbol. If we require 0 or more occurrences, then we can go with star symbol. Next, recognition of tokens. For recognizing the tokens, we need to make use of a finite automata. Finite automata is a state diagram where if we are given with some input, how we are moving from one state to another state. So if we are given with source program as input, then how we are going to recognize the pattern which has been matched with the token. So we have already discussed about tokens in the previous session, like what type of tokens we are going to have in a programming language. That is either in any programming language we may have either identifiers or keywords or operators or special characters or numbers. So here how we are, that means for each and every token we are having some specific pattern as a regular expression. So we need to the given source program has been, the source program input string has been matched with this regular expression pattern, so that we can generate the token. Otherwise we cannot form the token. So how we are first of all we need to have an idea how we are going to match the pattern given string with the pattern. For example, this is a state transition diagram or the finite automata where we are going to accept all the strings which are ending with AB. So here the strings which can be ended with AB can be specified by means of, for example, the language contains the strings over alphabets over A and B, right? So that here we can form the language, we can form the strings over the alphabets A and B, means A, B, AB, AAB, BA, BAA and so on, right? But here the condition here is all the strings should end with AB. So that we should take AB. So here we may have, before this AB we may have anything. So 0 or more occurrences. Any character may or may not be there. So that we can take, it should be ended with AB. So here I am taking here A, here B, here combination of AB or combination of AA, right? Like this we can take. So here either, that means it should be ended with AB, so that we should write the finite automata, we should generate the finite automata, we should accept at least AB. So initially I am at Q0. Here the finite automata can be represented by using state machine or state diagram, so that if we are at the initial state, if we given with some input, so that it will go to the next state, that is Q1 I am mentioning, so that the next input is at least it should accept, we are going to generate a finite automata which should accept at least A and B. So it goes to Q2 state. So we can mention that as a Q2 state, as a final state. Why? Because we can this finite automata will take the smallest string in a given language, that is AB, because the A or B occurrences before this AB can be 0, right? So this will accept AB as the input. Then what about the remaining strings? So that either A can be, or we may have B, right? So so this will accept A, AB, 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 A, B. So this will accept all the strings which can be which can be ended with A, B. So that is about finite automata. So here we are in the that means how we are going to match the patterns. Suppose if we are having some set of strings, so how we are going to whether that string has been formed or not. For example, here if this is the finite automata which will accept all the strings which are ended with AB. But if I take ABA as my input string and I want to check whether this string is accepted by this given finite automata or not. So how we can identify? So that first we will take A as input, so either it can go to the same state or it can go to the next state. Yes, it has moved to the next state. But now we are at Q1, next the input symbol is B, so that we have moved to the Q2. Even though we have reached to the final state, one more input character is available in the given input string, so that we can say that this string is not accepted by this given finite automata. That means this is a given input string and this will form a pattern. That means by making use of this particular finite automata, we are generating some set of strings, right? So these strings will form a finite automata. What is regular expression? What is that regular expression? A or B star AB, A or B star AB, so that either A occurrence or B occurrence or both the occurrences can be done, but it should be ended with AB. So these are the compulsory. This AB means it should, in the given string, AB should be there and the remaining characters may or may not be there. So that only A can be there or B can be there or the combination of A and B can be there. So that we are going to specify this regular expression. This regular expression should be matched with this, then only that particular this regular expression is called as a pattern. So this can be matched with the given input string, then only we can say that the given finite automata will accept the given input string. But in this case, this will not match with the given regular this string given string is not matched with the specified regular expression, so that we can say that the given string is not accepted by the given finite automata. So as we have already discussed, in every programming language we are having some set of tokens, right? Identifiers, keywords, operators, special characters and numbers. For each and every token we are having a specific pattern called as a regular expression. So by making use of that regular expression, how we are going to generate the finite automata and how we are accepting the how we are going to accept the given string as a token or not. Suppose if we are given with a string, so that we need to check whether that particular string is either an identifier or a keyword. Okay, suppose in the given statement if we are having int count is equal to 0, so that here as we know that int is a keyword, count is an identifier, equal to is an operator, 0 is a number, right? So like that it will identify, the lexical analyzer will identify int as a keyword, count as a identifier, equal to as an operator, 0 as a number, right? So how it will identify is, first it will take int as input, int, as we have already discussed in the input buffer, input buffering, so that statement will be stored in the input buffer character by character. First int will be stored and will take, after that its white space has been encountered, so that will take only take an example, int count is equal to 0. Okay, this statement will be stored in the input buffer as int space COU like this it will store. Now we are having beginning pointer and forward pointer. So first time both beginning pointer and forward pointer will point to the starting character in the input buffer, so that every time if we are reading the next character in the input buffer, the forward pointer will be incremented by 1. Whenever the forward pointer will be at the white space, then it has identified that the string has been completed. So that this forward pointer will be decremented by 1. Now the characters in between forward beginning pointer and the forward pointer are I, N and T. This will be treated as a lexeme. This lexeme will be given to the finite automata, so that in the finite automata we are having some set of finite automatas for identifying the tokens, like one finite automata for identifiers, one for keywords, one for operators. Like that we are having different finite automatas. First this will be given to the keywords finite automata, or else here it will be taken. So here I will be given, yes. Next N, T, so that here either a letter or digit has been taken. The first should be for identifying whether the given string or the lexeme is an identifier or not. Will take the first letter should be, the first character should be letter. Yes, it's true. Why? Because I is a character, right? So I is a letter, so it will be accepted. Then T will be taken, so N will be taken, then T will be taken. But the thing is here int is a keyword, so that whenever a string, the lexeme has been formed, if it is a stream of characters, then first it will check with the keywords finite automata. So in every programming language we have been specified with some set of keywords, so that according to those keywords a finite automata has been generated for specifying whether it is a keyword or not. So if it is not matched with any of the keyword in the given finite automata, then it will go for the identifiers finite automata. So if it is here, even though it is it will be accepted by this particular finite automata, but int is a keyword, so that first we need to check whether whenever we are having a lexeme is a stream of characters, we should check with the keywords, then we should come for the identifiers. So this is the finite automata for identifiers. So identifier can be like if you take count, okay. So here this will be given as finite automata of keywords. So it will be matched, so that it will generate int as keyword 1. Then we'll go with, after that again forward point, and then this beginning pointer will be at this location. Both beginning pointer and forward pointer points to the same location. Now COUNT, and after that there is an operator. So here beginning pointer and then the forward pointer will be incremented by 1 every time, then the forward pointer points to equal to. So here there is a mismatch. Previously it is an alphabet and now it is an operator, so that whenever a white space or an operator has been encountered, then automatically the forward pointer will be decremented by 1, so that the characters in between the beginning pointer and forward pointer will be taken and that will be considered as a lexeme, and this lexeme will be given as input to the finite automata of identifiers. So what is the finite automata for identifiers? Initially we are at Q0. Okay. Whenever a letter has been encountered, then we are the first, an identifier means the first letter should be a letter, right? So then that will be given whenever a letter is there. Then the second character onwards, it may be either a letter or a digit. Then automatically we can go to the final state. So here we'll take COUNT as a lexeme, and that will be given to the finite automata. This is a finite automata for identifiers. So here, yes, the first character is C. C is a letter, and from second character onwards, O is a letter, true. Same state. Next U will be, if for Q1, if O is the input, then it will go to the same state, and if U is the input, it goes to the same state, N as well as T. So it will be repeated for until and unless T has been encountered. Whenever T has been completed, then automatically it goes to the final state, because no other symbol is there in the input buffer, right? So now we have reached to the final state and there is no symbol in the input buffer, so that we can say no symbol in the lexeme, so that we can say that this particular count is matched with the finite token, like it will be identified as an identifier 1, ID 1. So next, that will, in the same way, we are having some set of finite automatas for identifiers. This is the keywords. So here they have taken if, but for each and every keyword we need to specify all the keywords in this particular finite automata. For our simplicity, we have taken only if. This is the finite automata for identifiers, this is for keywords, and then this is for recognizing the numbers. So here, for how we are identifying a number, the given in the given statement, how we can say that it is a number. Like the number can be either the numbers can be formed by using from 0 to 9, right? By using the digits 0 to 9. But the number may be an integer or a floating or a decimal number, right? So or an exponential number. So that we need to take like here it can form. If it is an integer number, then it is digit star. So that if it is a single digit number, directly we are moving from state 8 to 9 and then final state. If it is a single digit number. If it is a multi-digit number, then the character, whatever the character we are reading, that can be a digit, and second character onwards it may be a digit. So this will be repeated for many number of times until and unless the digits has been computed in the statement. So that and then it will move to the final state. So this particular finite automata or this state diagram is only for the integer numbers. And if it is a floating point number, then floating point number can, in the floating point number before the decimal point we may have single digit or multi digits. So that this will be repeated, and then there is a dot operator, and again also we may have multiple number of digits. So that If it is an integer, only digits will be there. If it is a floating decimal number, then a dot operator will be there in between the digits. Okay. So here, before the dot operator, we are having some set of digits, and after dot operator also, we are having some set of digits. And this is for exponential numbers. So this is for exponential numbers. So if you want to represent any number either by using integer or floating point number or exponential number, and this is for white spaces or tab spaces or new line character. This is the finite automata for white spaces or tab spaces or new line characters. And this is for operators, relational operators. Not only for relational operators, we may have the finite automata for all the operators also. So whenever, if you are having a symbol greater than has been less than has been encountered, we need to check whether it is only less than or only greater than, or else along with this less than we may have equal to. If we are having only less than operator, suppose A less than B, so that we can say that it is a comparison operator. Less than, and directly we can move to the final state. If it is less than or equal to, so less than, equal to, then we can, after completing equal to, then only we can move to the final state. So sometimes we may have less than and greater than. Then also we can say we can move to the final state. Like this, we are having some set of finite automatas for recognizing the tokens, and these finite automatas are used in the Lex tool for identifying the tokens. In the next session, we are going to discuss about finite automata.